This is Premise Podcast number 51, and today we're talking about wind turbine blade design. And this is going to be a two-part podcast because there is so much stuff in here to cover. And so it's going to cover everything wind turbine blade design. So what they look like, how many there are, how it differs from different wind turbines, and the different wind turbines that are out there. And to do that, we're going to look at a review paper called Wind Turbine Blade Design. It's open access, so you can find the link in the description. So let's get on with it. So they're going to be covering the theoretical maximum efficiency, propulsion, practical efficiency, and all those other things. And they're going to talk about the difference between vertical axis wind turbines and horizontal axis wind turbines, and then go on to horizontal axis wind turbines. And they say, first of all, that horizontal axis wind turbines are the ones where the quintessential ones that you see all over the countryside, where you have a central tower going up. Then coming out of the tower, you have three blades that go around, as you'd find. The vertical axis wind turbine, that's where you have the tower going up, and then you have these blades that are also in the same direction, sort of like almost like an egg beater kind of thing, and then they go around that direction. They're fundamentally different. And the reason why they're fundamentally different, they say that the discontinued mainstream development of the vertical axis wind turbine, or VORT, it must be German, anyway, can be attributed to a low tip speed ratio and difficulty controlling rotor speeds. Difficulties in the starting of the vertical turbines have also hampered development, believed until recently to be incapable of self-starting. So I sense that there's a bit of a twist here. They're saying that it was believed until recently that they weren't able to self-start, and that's a big deal because you want your wind turbine to extract energy whenever there's wind around. You don't want to have to go and start it yourself and then get energy out of that. That's efficient. It wastes a bit of time and you don't get as much energy. So that's why horizontal axis wind turbines, or HORTs, are more popular than VORTs. However, the VORT requires no additional mechanism to face the wind, and heavy generator equipment can be mounted on the ground, thus reducing tower loads. So that's one major detriment of a horizontal axis wind turbine, where you have the tower going up. Then the shaft that these blades rotate around is horizontal now. And that means you need to have very big bearings, very strong gearbox gears in there to support this weight. And as the blades go around, obviously they change the direction that they're facing and also rotation speeds. That creates a lot more force on these gearing systems, and that can lead to a lot greater wear, whereas the VORTs don't have that problem. They say that the VORTs are not completely disregarded for future development. A novel V-shaped VORT rotor design is currently under investigation, which exploits the favorable conditions of these VORTs, which are a reduced wear on these gearing mechanisms and makes it easier overall just to build. So if there is a reduced load on the gearing mechanism, it indicates that that also probably be cheaper to make because you don't need to have as much material to make a gearbox or other features that you need to incorporate. So that's one benefit there. They say, in addition to the problems associated with alternative designs, the popularity of the HORT can be attributed to increased rotor control through pitch and yaw control. So we'll get into that later on, but effectively just they can change the angle that the blades are at so you can extract energy much more efficiently. The HORT has therefore emerged as the dominant design configuration, and you can see them everywhere over the countryside. In fact, seeing VORTs are almost like non-existent. They're a novelty when you do see them. Now, they go into the energy that you can extract from the air. And they say that the energy, which is carried by the moving air, is expressed as a sum of its kinetic energy. And this is pretty cool. It's amazing how often kinetic energy pops up in different areas in aerodynamics. So in podcast number 6, I talked about how the dynamic pressure is very similar to the kinetic energy. In fact, they're very strongly related. And that's one thing that most people don't realize. So go watch that podcast and you'll learn about that. But here as well, they said that the power of the air, or the energy carried by it, is equal to half the density times by the area times by the velocity cubed. And the reason why the velocity is cubed is because you have the v square from this kinetic energy side, then you have the additional velocity from the continuity side. So how much energy, how much mass there is of the air. And that's what the equation works out to be. They say that a physical limit exists to the quantity of energy that can be extracted. And that's independent of any design. So hot, you can only extract a certain amount of energy, a theoretical maximum. Usually the working maximum is far less than that. They say that the energy extraction is maintained in a flow process through the reduction of kinetic energy and subsequent velocity in the wind. So when you take out energy from the wind, the velocity of the air is going to reduce. So that means that the magnitude of the energy harvested is a function of the reduction in the airspeed over the turbine. And the reason why we have a limitation is because 100% extraction would imply a zero final velocity and therefore no flow going through. And I talk about this at length in podcast number 48. So we talk about wind turbines in that, and you can also watch that to learn more about this phenomenon, which is called Betz limit or Betz theory. I'll just briefly cover it here a little bit more. They say that the zero flow scenario cannot be achieved because all the wind's kinetic energy would be used and it would drop to zero, so the air wouldn't go through anymore. And there's actually a theoretical upper limit, which is 59.3%. I won't go into why that is in this podcast. Number 48, I go into it more. So this is called Betz theory or Betz limit. And this is also best case scenario as well. So they say that not only is 59.3% the best case scenario theoretically, but this theory assumes constant linear velocity. Therefore, any rotational forces, such as the wake rotation or the turbulence caused by the drag or vortex shedding from the tips, so these tip losses, will further reduce this maximum efficiency. So 59.3% is, even that is like a fantastic result, which is never going to get achieved. They say that energy efficiency losses are generally reduced by avoiding low tip speed ratios. We'll get into what that means later on, because these low tip speed ratios increase the wake rotation. They also say selecting airfoils which have a high lift to drag ratio, which makes sense. Again, we're going to cover that. And specialized tip geometries, again, to reduce the vortex shedding and the drag. And we'll get into that again. So they go through a history now of horizontal axis of wind turbines, which is quite interesting, and the different developments. So first of all, they say that the method of propulsion critically affects the maximum achievable efficiency of the rotor. So historically, the most commonly utilized method was drag. So instead of having these blades which produce lift and then that produces the rotational force and makes the blades go around, it was just drag, a very simple idea where you put a sail or a block, like a flat plate or whatever, normal to the wind hits it, and then that force that the wind creates, drag, just moves this object around. And they say historically, this was used by like facing a sail normal to the wind, and they rely on the drag coefficient to produce a force in the direction of the prevailing wind. This method is inefficient as the force and rotation of the sail correspond to the wind direction. Therefore, the relative velocity of the wind is reduced as the speed increases. So what that means is, as the speed of this wind turbine increases, obviously the flat plate that is facing the wind is now moving quicker, and it's matching the wind velocity. So that means that the drag reduces, so you can't go faster. If you were to go faster than the wind, you'd actually be imparting energy to the wind, which is the exact opposite of what a turbine does. That's why you can't increase the velocity. There's a very strong ceiling there. Alternatively, wind turbines that use lift to produce the rotational force are not limited by that factor. And interestingly, the maximum theoretical efficiency of a wind turbine that uses drag is only 16%. 16. So 1/6 of 100%. Ones that use lift, as I mentioned, Betz theory or whatever, generally 50 to 60% is the theoretical upper limit. In practice, it's a little bit lower than that because of losses, but it's far better than using drag. And that's why lift wind turbines are a lot more desirable for producing lift, for producing energy, or gaining energy, I should say. They say that these drag wind turbines, they're inefficient power producers as their tip speed ratio cannot exceed 1. So they can't go faster than the flow. And then about 700 years ago, that's when we started using aerodynamic lift to produce usable energy or work. And this started in windmills. and then later in vintage aircraft. So they say for a lift-driven rotor, the relative velocity at which the air strikes the blade is a function of the blade velocity at the radius under consideration and approximately 2/3 of the wind velocity. So let's describe this in normal words. So when you have the blade going around, imagine you're on a blade. Now, even though you have the free stream velocity hitting you, because you're moving relative to the air, that air is now coming at a different angle. And that means that the relative velocity is a function of not only the free stream velocity, but also the blade velocity. So let's get into the efficiencies. In practice, rotors suffer from the accumulation of minor losses resulting from tip losses. So that's like vortex generation. So for akin to induced drag in aircraft, wake effects, drivetrain efficiency losses. So that's where you have the gear box not performing properly. Well, there's obviously going to be some losses there, but if you have a inadequately designed gearbox, and you gave them more losses. And the blade shape simplification losses. So if you know what the blade should be, but you simplify it because it's easy to manufacture, that's going to result in losses. So there's a trade-off between whether you want to have the best efficiency possible or a cheaper wind turbine. And then they have a really cool table here. As I mentioned, this paper is really good. You should download it and read it yourself because there's a lot of information in here. This table is indicative of that. So they say they have modern and historical rotor designs. So they have ones called Savonius rotors, and they are they're ancient designs, and they do have some interest these days, but that's mainly more research based than not really in practice. And they use drag, so they have like little plates that rotate around, and you generate the force through drag. And the maximum efficiency is 16%. In the modern day, like home application, have you ever seen these little weather stations that people put on like their porch or whatever, they're under their veranda to determine what the rainfall is, the temperature, and the wind is? And the wind device is a tiny little windmill, because what you have on there is the shaft going up, and then these little cups, 3 little cups, each one coming off at 120 degrees from the other, and then that creates drag, and it makes the cups go around, and then you can determine what the velocity of the wind is. That's another type that uses drag, and the peak efficiency is only 8%, so it's really terrible. Another type of wind turbine is the quintessential one that you see on American farms, from like the 1800s, where it's has like 20 blades or so, and then there's like this sort of arrow thing coming out from the side. And they actually they use lift to produce the rotational force, and they actually have an efficiency of 31%. So that's pretty damn good, considering that it's not really hasn't been designed in a wind tunnel. They were designed well before wind tunnels were around. And then you have the Dutch windmills. So everyone knows what a Dutch windmill is, where there's like that central, almost lighthouse structure, and then you have 4 big blades coming off, and most of the blade is actually not even filled in. It's just this cross-sectional area, this hatching area. And they use lift to produce the rotational force, and their efficiency is 27%. So that's pretty good as well. Then there's another wind turbine type called the Darius rotor, and that uses lift again. They have a maximum efficiency of about 40%, so that's getting better. And this came about during the 20th century. And then the modern wind turbine that we see everywhere, the horizontal axis wind turbines, the HORTs, they are the preferred choice, and their efficiency depends on, among other things, the number of blades that it has. So did you know you can actually get a 1-blade wind turbine, which I can't see how that would be any good for anything, considering that the loads on the gearbox would be horrendous as this thing goes around. But a 1-blade wind turbine has an efficiency of 43%, 2 blades 47%, and 3 blades 50%. So the more blades you have up to a certain point, the more efficient the wind turbine becomes. So speaking of efficiency, I'm going to quickly pause here and just talk about, if you want to increase the efficiency of your wind tunnel experiments, you need to make sure to measure the density of the air that you're using in your wind turbine, in your wind tunnel, sorry. We've been talking about wind turbines too much, in wind tunnel. And the reason why that is important is because the density affects everything in your measurements. They affect the Reynolds number, they affect even the wind tunnel velocity. So if you want to determine what the wind tunnel velocity is, you need to know what the density is. And the density can change 2 or 3% on a regular day. Now we have a device that gets rid of that problem for you. And it prints the density that it measures on a big screen, so you can see it anywhere in your lab, and you can use your density reading to factor that in when you're doing your experiments to get rid of all these errors. And that makes your experiments far better. It makes it easier to process the data. It makes it easier to write papers about your results. It also makes it easy. It also reduces the amount of time you need to be in the wind tunnel, because now you have less errors. When you do an experiment, you're going to be getting far more repeatable results. So you don't have to do like 3 runs just to get a general idea. You can do 1 or 2 because your errors are now much lower. This is called the Atmosphere Hawk. Again, we make it here and it's awesome. Everyone needs one, and it plugs right into the power and it works straight away. There's nothing else you need to do. It's very simple to use. A child could figure out how to use it. Just plug it into the power. That's it. Link in the description. So let's move on with the rest of the podcast. So they go into the Hort blade design. First of all, they say that this section briefly discusses the major parameters that influence the performance of Hort blades. The first one is tip speed ratio. So the tip speed ratio is defined as the relationship between the blade rotor velocity and the relative wind velocity. And they say it's the most important parameter to optimize the rotor dimensions. And there's a very simple equation here. It's just the tip speed ratio equals the rotational velocity of the blades times by the radius of the blades divided by the wind speed. And they say that the efficiency of the tip of the turbine can be increased with higher tip speeds, although the increase is not significant when considering some penalties such as increased noise, aerodynamic and centrifugal stresses. So they have a nice table here where they say when the tip speed ratio increases, the efficiency dramatically increases. However, there's a certain limit. Above a tip speed ratio of 8, the increase in efficiency is negligible. Now, when you lower the tip speed ratio, the efficiency drops. And they say that it decreases significantly below 5 due to rotational weight created by high torque. Now, one thing that's interesting is the noise of a wind turbine, of a Hort at least, is proportional to the 6th power. So what that means is that the noise generated by a wind turbine dramatically increases with increasing tip speed ratio. So if you increase tip speed ratio by just a little bit, the noise just goes through the roof. They say that a high tip speed ratio demands reduced chord widths, leading to narrow blade profiles. This can lead to reduced material usages and lower production costs, so that's good. However, an increase in centrifugal and aerodynamic forces is associated with high tip speeds. So that makes sense. If you have something rotating around faster, there's going to be more loading on the gearbox and the bearings and all that. So then you might have to reinforce them, and that makes production go higher. The production costs go higher. They say the increased forces signify that difficulties exist with maintaining structural integrity and preventing blade failure. As the tip speed increases, the aerodynamics of the blade design become increasingly critical. A blade which is designed for high relative wind speeds develops minimal torque at lower speeds. So that means that there's a higher cut-in speed and the difficulty to self-start increases. So what this means is if you design your wind turbine to operate at very high tip speeds ratios, that means that you need to have a very strong wind just to get it started. And if you don't have that strong wind, it's going to sit there like a sack of rice doing nothing. So that's one thing to keep in mind. They also say, as I mentioned, the noise increase is associated with increasing tip speeds and is approximately proportional to the 6th power. So I'm guessing that's something to do with Little's equation. I'm not going to go into that here because that's a beast in itself. They say that modern Horts generally utilize a tip speed ratio of 9 to 10 for 2-blade rotors and 6 to 9 for 3-blade rotors. This has been found to produce efficient conversions of the wind's kinetic energy into electric power. So let's talk about the blade shape and quantity. We talked just then that if you have 2 blades compared to 3 blades, the tip speed ratio that you want to use is a little bit different. So first of all, for blades with tip speed ratios of 6 to 9, utilizing airfoil sections with negligible drag and tip losses, Betz momentum theory gives a good approximation. However, with low tip speed ratios, high drag airfoil sections and blade sections around the hub, Betz momentum theory is now inaccurate. So it's really just an approximation of Betz theory, not the rule. So in such cases, wake and drag losses should be accounted for, which Betz's momentum theory does not account for. And they say the Betz's method gives the basic shape of the modern wind turbine blade. So that's quite nice. And there's a very simple equation here. I'm not going to go through it. If you want to look at it, you can look at this paper. It's very simple. And in figure 2, they have a typical blade plane and regional classification. So first of all, the blade, which approximates an airfoil for a aeronautical purpose, the nomenclature is a little bit different. So the tip, if you were to look at the wing on an aircraft, when you refer to the tip, it's pretty much the very end of it. Whereas the tip on a wind turbine blade accounts for about 20% of the end. So it's quite a lot. Likewise, on an airplane, the root of a wing is really where it just meets the fuselage. Whereas in a wind turbine blade, it accounts again for about 20% of the entire span. And then the rest of the wind of the blade is called midspan. Now, let's talk about the design of this blade. So the midspan and the tip are reducing in chord fairly linearly. So at the point where the midspan starts, which is about 20% from the point where the blade joins the hub, the chord is a certain length. And as you go towards the tip, the chord gently reduces, which is what you expect. However, at the root, you have the chord gets a little bit thicker before getting very thin and then meeting the hub. So that's a little bit different. You might expect that the chord should just be continually getting larger and larger as you meet the hub, but there's this drop off. They say that assuming that a reasonable lift coefficient is maintained, utilizing a blade optimization method produces blade plans, principally dependent on design, tip speed ratio, and number of blades. So in figure 3, so let's look at that. So figure 3 is pretty cool. They have the optimal blade plan shape for alternate design, tip speeds, and number of blades. And what we can see quite easily is as you increase the number of blades, no matter what the tip speed ratio is, the chord will reduce. That's the best way, that's the most efficient way. What's more, as you increase the tip speed ratio, the blade chord should also reduce. So if you have more blades or they go faster, you should reduce the chord. And then once you get to 4 blades and tip speed ratio of 15, the blades are pretty much just like a needle. So they say low tip speed ratios produce a rotor with a high ratio of solidity, which is the ratio of the blade area to the area of the swept rotor. It is useful to reduce the area of solidity as it leads to a decrease in material usage and therefore production costs. It also affects the efficiency as well. So now they have figure 4, how simplifying a wind turbine blade affects the efficiency of the blade. And the ideal case, which is quite difficult to manufacture, that's obviously the best. But then you want to perhaps make simplifications to make manufacturing costs lower and make it easier. And one example is when you sort of make an arrow type head. So if you imagine like an arrow head and then you just stretch it, that is a fairly good approximation of the most ideal chord, the most ideal general plan form. But doing so reduces the efficiency by about 0.2%. So that's still pretty decent. However, that may be too difficult to manufacture. So if you want to make it easier, you might be able to take off those edges to the arrowhead. You know how it flares out. Take those edges off and round them. That reduces the efficiency by 1.5%. Then if you want to make it even simpler, you just make the entire chord pretty much constant across the span, and that reduces efficiency by 8.1%. So that's obviously easy to make, but the efficiency drops. They say for optimum chord dimensioning, the quantity of blades is considered negligible in terms of efficiency. However, in practice, when blade losses are considered, a 3% loss is incurred for 2 blade designs and a 7 to 13% loss for 1 blade designs when compared to 3 blades. And then they say a four-blade design offers a little bit more efficiency, but not enough to justify manufacturing costs. And they also say tower loading must also be considered when choosing the appropriate blade quantity. 4, 3, 2, and 1-bladed designs lead to increased dynamic loads respectively. And that makes sense. I mean, when you have more blades spaced equally around a rotational axis, the forces, the rotational forces are well balanced. As you reduce the number of blades, this balancing becomes worse. And then when you have one blade just going around, the balancing is terrible. I mean, I'm surprised wind turbines could even operate like that without breaking in like 2 seconds. So the imposing size and location of wind turbines signify that the visual impact must be considered. However, I think that they look pretty good. I mean, not to put them everywhere, like not to put them in your backyard or whatever. Although having one in your backyard looks pretty decent. But having them on mountains and hilltops on those ridges, they look quite cool when you drive around. Yeah. So three-bladed designs are said to appear smoother in rotation, therefore more aesthetically pleasing. So in other words, people think that three-bladed designs look better than any other design because they are smoother when they rotate and they're more symmetrical when they look. Faster one- and two-bladed designs have an apparent jerky motion. Three-bladed rotors are also thought to appear more orderly when in their stationary position. So they look nicer, and I agree. So let's talk about the configuration. A favorable reduction in rotor nacelle weight and manufacturing costs occur with the use of fewer blades. However, dynamic structural and balancing difficulties of the polar asymmetrical rotor are apparent. So what this means is, let's use English here. So what that means is when you reduce the number of blades, you get asymmetry in forces that are being put onto the central shaft, which then means that the nacelle needs to be stronger in general. And that means you have to increase production costs. This increases wear and inferior aesthetic qualities and bird conservation problems, are also associated with one- and two-bladed rotors. So that's interesting. Apparently, one- and two-bladed rotors kill more birds than three-bladed rotors. I didn't know that. Actually, this reminds me of one thing that I remember. It's good for engineers to keep in mind. So I remember when I was back doing my undergrad degree, and we were learning about aircraft, and the lecturer was saying, well, should an airplane be designed to withstand a bird strike? And most people were like, yeah, well, there are birds in the sky, so it probably should be. And then he goes, well, how many airplanes have you heard that have been hit by birds and gone down? And we were like, none. And he says, well, that's because, so then why should you design for it? That is a very bad, that is not very illogical. That's a very bad way of thinking about it. The fact is that airplanes are designed to withstand bird strikes. The reason why you don't hear airplanes going down from bird strikes is because they're designed not to. So saying that because you're not aware of any of these situations happening, doesn't mean that they haven't been designed to withstand them. That's why you don't hear any situations happening. I just thought I'd say that because I remember that very vividly. And it's good to keep in mind as an engineer. So let's move on. The three-bladed turbine has been widely adopted as the most efficient design to meet environmental, commercial, economic constraints, and therefore dominates today's large-scale wind turbine industries. And in Figure 5, they have like a two-scale model of a wind turbine hub to the nacelle and a human. I imagine it's a full-scale human on Oompa Loompa. And compared to the human, it's massive. I mean, we all know that wind turbines are huge, but this nacelle is like really big. It could fit like probably 50 or 60 of these guys in there. So it's really small. It's really big. So let's move on. Let's talk about the aerodynamics. This will be the last section we talk about for this podcast, and we move on to the other sections in the next podcast. So aerodynamic performance is fundamental for efficient rotor design. Aerodynamic lift is the force responsible for the power yield generated by modern turbines. Obviously, you can have drag-based turbines, but in modern days, we use lift-based turbines because they're far more efficient. And therefore, it is essential to maximize this force, the lift, using appropriate designs. The resistive drag force, which opposes the motion of the blade, is also generated by friction, which must be minimized. It also is by profile drag in general, so pressure drag, friction, and induced drag. It is then apparent that an airfoil section with a high lift-to-drag ratio, typically greater than 30, be chosen for rotor blade design. And the reason why I'm quite surprised by that is that having a lift-to-drag ratio, which is the measure of efficiency for an airfoil, of 30 is really good. I mean, to think about how good this is, if you get a typical airfoil, like a very basic one, let's say a NACA 0012 or a NACA 0021, or just a basic one, but a really good one still. I mean, they've been around for 70 years, and there's a reason why they've been around for 70 years. They are good for how simple they are. They have lift-to-drag ratios of about 20, depending on the Reynolds number. So to have 30, that's a really good airfoil, and obviously you need to put a lot of design into it to get such a lift-to-drag ratio. But they're really pushing the boundary here. They said traditionally airfoils are tested experimentally with tables correlating lift and drag at given angles of attack and Reynolds numbers. And historically, wind turbine airfoil designs have used these from aircraft manufacturers and that knowledge with similar Reynolds numbers and section thicknesses suitable for the conditions at the blade tip. So what they're saying is, historically, wind turbine blades were optimized for the blade tip velocity. Now that's a problem because they say that special considerations should be made for the design of wind turbine specific airfoil profiles at all the different operating conditions and along the blade, along the span. So very close to the hub, the root, the velocity of the relative velocity at this point that the blade sees is very different to at the tip. So you can't really have the same airfoil and expect the same performance. So that introduces inefficiencies. What's more, the effects of soiling have not been considered by aircraft airfoils, as they generally fly at altitudes where insects and other particulates are negligible. Turbines, on the other hand, operate for long periods at ground level where insects and dust particulate build up is problematic. So this fouls the blades and can have detrimental effects on lift generated. Obviously, they usually will. Although I imagine you could probably design a blade that where it can actually get better, but the initial condition would be worse overall. So provisions are therefore made for the reduced sensitivity to fouling of wind turbine specific airfoil designs. Now, the structural requirements of turbine blades signify that airfoils with a high thickness to chord ratio be used in the root region. Such airfoils are rarely used in the aerospace industry. Thick airfoil sections generally have a lower lift-to-drag ratio, and that's generally true. Special considerations are therefore made for increasing the lift of thick airfoil sections for use in wind turbine blade designs. So NACA, which if you haven't, or if you do know even about NACA airfoils, they're kind of like the benchmark that everyone just goes to and uses them, and they build off that often. And we have on our YouTube channel quite a few videos where we simulate NACA airfoils and we talk about all the aerodynamics of it, the pressure distributions, the lift and drag reductions, and the drag breakdowns to pressure drag and friction drag, and how that changes with Reynolds number, term density, and angle of attack. So check them out on our podcast, on our YouTube channel. We have a playlist with them on. And they say that the NACA airfoils, so 4 and 5 digit designs, have been used for early modern wind turbines. However, they are not designed for wind turbine use. They're designed for aircraft use. So they're not exactly 100% efficient for wind turbines. As a result, the emergence of wind turbine specific airfoils, such as the Delft University LS Series N REL and FFA and RISOs, now provide alternatives specifically tailored to the needs of the wind turbine industry. They say the use of a single airfoil for the entire blade length will result in inefficient design because the conditions that each part of the blade sees is different. So each section of the blade has a differing relative air velocity and structural requirement, and therefore should have its airfoil section tailored accordingly. At the root, the blade sections have a larger maximum thickness, which is essential for the intensive loads carried, resulting in thick profiles. Approaching the tip, blades blend into thinner sections with reduced loads, higher linear velocity, and increasingly critical aerodynamic performance. The differing airfoil requirements relative to the blade region are apparent when considering airfoil velocities and structural loads. So this is quite interesting. They have a table here, and they say the airflow requirements for blade regions. So at the root, the thickness to chord ratio should be greater than 27%, which is really thick. Mid-span should be 27 to 21%. Again, that's still very thick. And even the tip, 21 to 15%, is still very thick. But obviously, as you get closer to the tip, the thickness should reduce. All these thicknesses, however, are almost unimaginable for the aeronautical industry. Like that, they're just way too high, usually looking at about 12% or so. But for wind turbines, this is what you need to get maximum efficiency. This shows how these two industries are different. So an aerodynamic phenomenon known as stall, as we all know, should be considered carefully in turbine blade design. Stall typically occurs at large angles of attack depending on the airfoil design. And also depending on the airfoil, the stall pattern changes. And again, on our podcast, on our YouTube playlist, we go through how the stall changes with different airfoil profiles as you increase angle of attack. They do change very dramatically. So they say the boundary layer separates at the tip rather than further down the airfoil, causing a wake to flow over the upper surface, drastically reducing lift and increasing drag forces. This condition is considered dangerous in aviation and is generally avoided, and that's true. The reason why is because in aviation, we usually have our control surfaces outboard, so near the tip. And if you lose control of these control surfaces, then you're screwed. So you want to make sure that if anything stalls, it's going to be the inboard section first. Obviously, you don't want stall, but if it does happen, you want to make sure that happens first. So this you have control and you can get the airplane under control again and back to good operating conditions. However, for wind turbines, stall at the tip can be utilized to limit the maximum power output to prevent generator overload and excessive forces in the blades during extreme wind speeds, and could also occur unintentionally during gusts. It is therefore preferable that the onset of the stall condition is not instantaneous for wind turbine airfoils, and this will create excessive dynamic forces and vibrations. So in other words, you don't want the entire blade stalling at the same time. You want to have certain areas stalling first to gently introduce this different loading on the gearbox and the nacelle. If it all stalls at once, you get a dramatic change in force, and that could even result in something called flutter, which we go into as well in this podcast and other podcasts. But this happens in many other situations, and that's when the load changes so much that it creates this instability that just grows and it can destroy things. So the use of modern materials with superior mechanical properties may allow for thinner structural sections with increased lift-to-drag ratios at the root sections. Thinner sections also offer a chance to increase efficiency through reducing drag. Higher lift coefficients of thinner airfoil sections will in turn lead to reduced chord lengths, reducing material usage. So that's where I'm going to end this podcast today. For the second part, check in 3 days' time, and that will be uploaded for you. And make sure to like, subscribe this, and share this with any of your friends who are doing wind tunnel or wind turbine research or just interested in wind turbines. And also check out our atmosphere hawk, which every analyst needs to measure the density of their air that they're using accurately. This is important for, everything. Like if your density is not accurate, then your research is crap. I'm just going to say that. So make sure to check it out. Link in the description. Peace out, amigos.